Welcome to our lesson on weather information. This is one of the most important topics in aviation. Understanding weather is about staying safe. We'll walk through the fundamentals of weather theory, common hazards, and how to interpret and access the many sources of weather data available to pilots. We'll also look at key services and tools to help you make sound decisions before and during flight. Whether you're flying VFR on a clear day or navigating changing conditions en route, your ability to read and respond to weather is a core part of being a competent pilot. Let's start by looking at why weather information matters so much. As the pilot in command, the 14 CFR 91.103 makes it your responsibility to know all information relevant to the flight, including current and forecast weather. This isn't optional, it's a legal and safety requirement. A good weather briefing gives you the situational awareness to anticipate problems and avoid surprises. It helps you decide whether the flight is a go or a no-go, and it gives you a plan for what to do if things change while you're airborne. Let's dig into some weather theory. It all starts with the sun. The uneven heating of the Earth's surface is what causes wind. Land, water, and terrain absorb and release heat differently, creating temperature differences, which lead to pressure differences. And air moves from high pressure to low pressure. That's your wind. Let's begin with some definitions. You will often hear the term standard atmosphere, which is our baseline conditions from which we assess weather. At sea level, standard temperature is 15 degrees Celsius, or 59 degrees Fahrenheit. Standard pressure is 29.92 inches of mercury, or 1013.2 millibars. As you climb, the temperature typically drops about 2 degrees Celsius per 1,000 feet, and pressure drops about 1 inch of mercury per 1,000 feet. This pattern holds up to the tropopause, which is the boundary between the troposphere and stratosphere. It's about 20,000 feet high over the poles and can go up to 60,000 feet near the equator. Another important concept to know is the stability of the atmosphere. In a stable atmosphere, the temperature drops more slowly with altitude than the standard 2 degrees Celsius per 1,000 feet. This usually means smooth air and widespread low clouds. Think of stratus layers. In an unstable atmosphere, temperature drops faster than standard. That promotes rising air, which leads to vertical cloud development, like cumulus clouds, and often turbulence. Let's continue building our understanding of weather by looking at cloud types and pressure systems. Clouds are categorized by their altitude. High clouds form from about 16,500 to 40,000 feet and include cirrus types. Middle clouds range from about 6,500 to 23,000 feet and often include altostratus or altocumulus. And low clouds, which we encounter most often in GA flying, sit below 6,500 feet. Think stratus or cumulus layers. Cloud type gives us clues about the stability of the atmosphere and potential weather. For example, towering cumulus clouds often signal instability and turbulence, while stratus clouds indicate more stable conditions. When it comes to pressure systems, we can make a distinction between two kinds of systems: high pressure and low pressure. High-pressure systems are typically associated with descending air. That air pushes outward and downward, which is often associated to clear skies and good weather. On the other hand, low pressure pulls air inward and upward, encouraging cloud formation and precipitation, often leading to poor weather conditions. A trough is an elongated area of low pressure and often brings unsettled weather. A ridge is the opposite, an area of higher pressure that usually brings better conditions. It's also worth noting how wind behaves around pressure systems. Aloft, winds tend to flow parallel to the isobars due to the Coriolis effect. But closer to the surface, friction causes them to angle slightly into the low and out of the high. Let's move on to fronts, the boundaries between different air masses. We'll start with cold fronts. These move fast, typically around 30 miles per hour, and act like a snowplow, lifting warm air up quickly. This abrupt lifting often produces towering cumulus clouds and can lead to thunderstorms. If two cold air masses collide rapidly, especially if one is very fast-moving, you might get a squall line, which is a narrow band of intense storms. Next, we have warm fronts, which move more slowly, about 10 to 25 miles per hour. These have a gentle slope, usually approaching from the above, and typically bring widespread stratiform. Clouds, fog, and steady precipitation like rain, sleet, or snow. Visibility can be poor for extended areas, and ceilings may gradually lower ahead of the front. A stationary front occurs when neither air mass is strong enough to displace the other. These can hang around for several days and bring a mix of weather from both cold and warm fronts. Finally, occluded fronts form when a fast-moving cold front overtakes a slower-moving warm front. In a cold front occlusion, the advancing cold air is colder than the air ahead of the warm front, lifting everything in its path. This creates a blend of cold and warm front weather. In a warm front occlusion, the overtaking air is actually warmer than the cold air ahead, which can cause embedded thunderstorms and complex weather patterns. Let's talk briefly about how weather affects your altimeter, which is a key safety consideration in flight. First, remember, your altimeter is calibrated based on the standard atmosphere. If the actual conditions deviate from standard, your altimeter will not read your true altitude. When the air is colder than standard, the pressure lines in the atmosphere become closer together. As you know, all your altimeter does is to read the external pressure and show you what is the altitude based on a standard temperature. If the pressure is lower, the altimeter will show that you are higher, even though the low pressure is not caused by altitude, but by low temperature instead. In other words, your altimeter will tell you that you are higher than you actually are if you are in a cold area. A good rule of thumb is, for every 10 degrees Celsius below standard, your true altitude is about 4% lower than indicated. Here's an example on how to use this. Let's say you are flying at 10,500 feet and there is a mountain of 10,000 feet ahead of you, so you expect to clear it by 500 feet. However, the temperature is 10 degrees Celsius below standard, which means, by using the 4% rule, that you are actually flying at 10,080 feet, which is lower than what your altimeter indicates. You will be clearing the mountain by only 80 feet. Okay, so temperature is one area of concern. The other situation to be mindful of is when you fly from an area of higher pressure to lower pressure and forget to adjust your altimeter. In that scenario, you intend to fly at constant altitude. But remember, your altimeter is just reading the external pressure, so, in fact, you are not flying at constant altitude, but at constant pressure instead. Well, if you are now in an area of lower pressure and you haven't adjusted your altimeter, you are now lower than you think. That's where the old saying comes in handy. High to low or hot to cold, look out below. This error becomes more significant the higher you go. More altitude means more air below you, so the pressure difference has a greater impact on your actual altitude. This is especially important in mountainous areas or during IFR operations. Always adjust your altimeter setting based on updated pressure reports, and be cautious when flying in cold environments or transitioning into low-pressure areas. Now let's talk about some of the common weather hazards that can affect your flight, starting with inversions and turbulence. An inversion happens when temperature increases with altitude, which is the opposite of the normal lapse rate. When this occurs, it traps cooler, denser air near the surface. That can lead to wind shear at the inversion boundary. Turbulence, a term we hear a lot, can be of different types, such as frontal turbulence, which is the collision of air masses, mechanical turbulence, caused by terrain or man-made structures, thermal turbulence, caused by rising of warm air, and wind shear, which can occur with rapid changes in wind speed or direction. We also classify turbulence based on intensity. Light turbulence causes slight momentary changes in altitude or attitude. Moderate turbulence causes more noticeable changes, including fluctuations in airspeed, but you still have positive control. Severe turbulence involves large, abrupt changes in attitude, altitude, and airspeed. It also causes the aircraft to be momentarily out of control. Extreme turbulence is violent. It may cause structural damage and makes control nearly impossible. One specific type to be aware of is clear air turbulence, or CAT. This typically occurs above 15,000 feet, often near the jet stream, and, importantly, is not associated with any visible clouds. That means you can't see it coming, so knowing where jet streams are and checking upper level forecasts can help you avoid it. Another type to be aware of is the mountain wave turbulence. When strong winds blow across mountain ranges, the air on the downwind side can form waves that extend for hundreds of miles. If you see lenticular clouds, which are lens-shaped clouds that sit stationary even as the wind howls past, be cautious. That is an indication of mountain waves, and turbulence can be extreme beneath or downwind of them. Another major weather hazard is wind shear, a sudden sharp change in wind speed and/or direction over a short distance. You can feel it horizontally or vertically, and it's especially dangerous on takeoff and landing when you're close to the ground and have little room for recovery. Wind shear can cause rapid gains or losses in airspeed, sometimes as much as 30 to 90 knots. It can also create violent updrafts or downdrafts up to 6,000 feet per minute. That can seriously disrupt your flight path or even lead to loss of control. One of the most dangerous forms of wind shear is a microburst. These are small but intense downdrafts, usually 1 to 2 miles across, that slam into the ground and spread out in all directions. They can develop rapidly and are very difficult to escape once you're in them. So how do we detect wind shear? Some signs include virga, or rain that evaporates before reaching the ground, blowing dust near thunderstorms, and pyreps reporting sudden changes in airspeed or altitude. When wind shear is suspected or forecasted, here are some good techniques if you can't avoid it. Fly a slightly higher approach speed and stay higher on the glide path if possible. Be ready to go around at the first sign of shear. Use full power and establish a maximum performance climb if needed. The key is to recognize the risk early and take action decisively. Wind shear isn't something to try and power through. It's something to avoid or escape. Now let's talk about fog and freezing rain, two hazards that can sneak up on you quickly. Fog forms when air cools to its dew point, reducing visibility to less than 5/8 statute miles. There are several types of fog, and it's important to know the differences. Radiation fog is the most common. It forms on calm, clear nights when the ground cools quickly, cooling the air above it. Advection fog happens when moist air moves over a cooler surface, like along a cold coastal region. Steam fog occurs when cold, dry air moves over warmer water. You'll often see this over lakes or rivers in the early morning. Upslope fog forms when moist, stable air is forced up sloping terrain. As it rises, it cools to its dew point and condenses. There's also precipitation fog, which forms when warm rain falls through cooler air below, saturating it. Now, let's look at freezing rain, a serious in-flight hazard. It forms when warm air aloft causes rain to fall through a layer of cold air. That rain becomes supercooled and may freeze on contact with the aircraft, rapidly creating clear ice. Sometimes you'll see ice pellets hitting the ground. That's often a clue that freezing rain is occurring at altitude above your location. This type of weather is extremely dangerous. If you suspect freezing rain or see signs like ice pellets or embedded thunderstorms, it's time to divert or avoid that area entirely. Sometimes you can escape from freezing rain by climbing into the warm air above. However, it's often difficult to know where the warm air is, and your airplane might be iced up before you reach there. Since we are talking about icing now, let's dig deeper. Icing can affect multiple systems. Induction icing can block the air intake. Carburetor icing, which is a specific type of induction icing, can occur even in clear air with temperatures between 10 degrees Fahrenheit and 100 degrees Fahrenheit. Instrument icing is especially related to pitot-static systems. And of course, we also have the structural icing, which forms when visible moisture contacts surfaces of the airplane at temperatures below 0 degrees Celsius. There are 4 types of structural ice you should know. Clear ice forms from large, supercooled droplets that spread out and freeze slowly. It's heavy, smooth, and can form horns along leading edges, most common in cumuliform clouds, or freezing rain, usually between 0 degrees Celsius and minus 10 degrees Celsius. Rime ice is the most common. It forms instantly, trapping air bubbles and creating a rough, milky surface. It's lighter and usually forms in stratus clouds between -10 degrees Celsius and -20 degrees Celsius. Mixed ice is exactly that, a combination of rime and clear. It's irregular, heavier, and harder to remove. And frost, which forms on the surface when the temperature is below the dew point, and both are below freezing. Even a thin layer can disrupt airflow and seriously degrade lift. Icing intensity is categorized like this. Trace, barely noticeable, but it is an important indication that icing conditions are present. Light, may require occasional use of de-icing or anti-icing equipment. Moderate, means action is needed. De-icing systems must be active, and diversion may be necessary. Severe, means de-icing equipment can't keep up. You must exit those conditions immediately. Always check for visible moisture and temperature before entering any cloud layer in cold air. If both are present, there's a risk of structural icing. Let's finish the hazards section with thunderstorms, the most violent type of weather we deal with in aviation. Three ingredients are needed to form a thunderstorm: moisture in the air, unstable air, where temperature decreases rapidly with altitude, and a lifting force, like frontal movement, heating from the surface, or terrain. Thunderstorms come in three types. Single-cell storms are short-lived and fairly isolated. Multi-cell storms are clusters of thunderstorms that form and dissipate in cycles. Supercells are large, rotating storms with intense updrafts. They're the most dangerous and can produce severe turbulence, hail, and tornadoes. The three stages of a thunderstorm are developing, characterized by updrafts; mature, the most dangerous stage, with strong updrafts and downdrafts, precipitation, lightning, and turbulence; and dissipating, dominated by downdrafts, but still hazardous. Thunderstorms can contain threats such as low visibility, strong turbulence, icing, hail, downbursts, microbursts, and clear air turbulence well above the visible clouds. Avoid thunderstorms by at least 20 nautical miles, especially on the downwind side. A small aircraft is not built to withstand the full force of a thunderstorm. All right, let's shift gears and talk about where to get weather information, both on the ground and in the air. On the ground, we have several great tools. Leidos Flight Service at 1800weatherbriefing.com. Flight Service Stations, the Aviation Weather Center, which includes the GFA tool. National Weather Service and the Storm Prediction Center, and apps like 4Flight. In the air, we have options like Flight Service, nearby stations for surface observations, SiriusXM and onboard radar systems, lightning detectors, ARTCC broadcasts, and PIREP reports, FISB, available via ADSB-IN. Now let's take a deeper look into the weather products available to pilots, starting with AirMets and SIGMETs. AirMets are issued for weather that is relevant to all aircraft, and may be hazardous, particularly to light aircraft. They come in three types: Sierra for IFR conditions and mountain obscuration, Tango for moderate turbulence, surface winds over 30 knots or low-level wind shear, Zulu for moderate icing and freezing level information. AirMets are issued every 6 hours, and while they're generally less severe than SIGMETs, they still require attention, especially when flying in a smaller or less capable aircraft. SIGMETs report non-convective weather that is potentially hazardous to all aircraft, not just small ones. Examples include severe icing, severe or extreme turbulence, clear air turbulence, and volcanic ash, or dust storms. These are unscheduled and valid for 4 hours when published, or 6 hours if covering volcanic ash or tropical cyclones. Convective SIGMETs are issued every hour for hazardous weather related to thunderstorms, including surface winds greater than 50 knots, hail greater than 3/4 inch, tornadoes, severe turbulence, icing, low-level wind shear associated with thunderstorms, squall lines, and embedded storms. All of these advisories are accessible via FISB, Flight Service, or apps like 4Flight. Make a habit of checking them during pre-flight and monitoring updates in flight when conditions warrant it. MEDARs are aviation routine weather reports issued every hour or as a specky if there's a significant weather change between routine updates. These reports give a snapshot of current surface weather conditions: wind, visibility, sky condition, temperature, dew point, altimeter setting, and any significant weather phenomena. Winds aloft forecasts are issued 4 times a day and provide wind direction, wind speed, and temperature at various altitudes. You'll typically see these in either table or graphical format, depending on your tool. Just note that winds aren't forecast within 1,500 feet AGL, and temperatures aren't included within 2,500 feet of station elevation. These forecasts are especially useful for planning fuel burn, time en route, and turbulence avoidance at cruise altitudes. TAFs are issued every 6 hours and provide a forecast for a 5 statute-mile radius around an airport. They're valid for either 24 or 30 hours, depending on the site. TAFs are a core part of pre-flight weather planning, especially when assessing alternate airport requirements under IFR. Another tool you might see is MOS, Model Output Statistics. MOS is an automated forecast based on statistical models and past trends. It's not considered an official FAA weather source, but it can help fill in the gaps, especially at smaller airports without TAFs. You'll often see MOS data on platforms like 4Flight. Now let's touch on satellite weather, which gives you the big picture view. There are 3 main types of satellite imagery. Visible satellite shows actual images, kind of like photos from space, great for spotting cloud patterns during daylight. Infrared imagery measures the temperature of cloud tops, helping estimate altitude. High clouds tend to be cooler and appear bright white, while lower ones are gray or dark. Water vapor imagery shows areas of moist and dry air. Satellite tools are excellent for spotting large-scale systems, fronts, and thunderstorm development. Significant weather charts are forecast products that show selected weather hazards at various altitudes. They're issued every 6 hours and show areas of marginal VFR, IFR, and icing levels. The surface analysis chart shows current conditions, pressure systems, fronts, and areas of precipitation, and it's updated every 3 hours. Prog charts show forecasts for the next 12 and 24 hours and longer range for 36, 48, and even 60 hours ahead. These charts help you track weather systems, like fronts and pressure areas, and anticipate how conditions will evolve across your route. Convective outlook comes from the Storm Prediction Center and shows areas where severe thunderstorms, with hazards like tornadoes, hail, or strong winds, are expected to develop. The outlook is issued multiple times per day for day 1, twice per day for day 2, and once per day for days 3 and beyond. Risk levels include marginal, slight, enhanced, moderate, and high. This is a great product to reference when planning cross-country flights during thunderstorm season. Even if storms aren't forecast right at your destination, convective activity anywhere near your route could impact your go-no-go decision. To wrap up our review of weather services, let's look at 2 powerful tools: the GFA tool and NEXRAD radar. First, the GFA tool, or Graphical Forecast for Aviation, available at aviationweather.gov, is an interactive map that consolidates a wide range of weather data in one place. You can toggle layers to view MEDARs, TAFs, ceilings, visibility, icing, turbulence, and more, all visualized across time and space. It's especially helpful for getting a big-picture view of your planned route and for spotting areas of concern. Next up is NEXRAD radar, short for Next Generation Radar. This is a network of Doppler radars that send out signals and measure the reflections, or echoes, that bounce back from precipitation. To be clear, radar shows precipitations, not clouds. They are usually together, but just bear in mind that the absence of rain does not mean absence of clouds. NEXRAD imagery is updated about every 10 minutes, and the reflectivity values, measured in decibel, indicate the intensity of precipitation. There are 3 types of radar products you'll typically encounter: base reflectivity, which shows the lowest elevation scan; top reflectivity, showing how high precipitation is reaching; and composite reflectivity, which displays the strongest returns at all scanned angles. Radar is incredibly useful, but not perfect. They do have limitations such as attenuation, blockage, and false echoes. Most important, if you are flying and getting NEXRAD information via ADS-B, know that what you are looking at is not real time. It usually has a delay between 15 to 20 minutes, and there were cases of pilots that unsuccessfully tried to circumvent a thunderstorm using this product as if it was real time, just to find themselves inside the cell. And that wraps our lesson today. Thanks for watching. And if you like this content, please consider subscribing. This will help us create more lessons like this.